Probability, a section that you all hate, or hate to love, or love to hate, whatever the case may be. This lesson is going to help you to understand probability in a much better and clearer way. And I tell you guys, if you listen to this lesson till the end, you will be able to do just about any question on probability. What I will not include, however, in this section at the moment, will be fundamental counting principles, right? We will do that next. Let's get right into it. Okay, so you can play it at 2 times the speed if you want to. Okay, that's really up to you. Okay, let's get right into it. So first of all, we talk about probability as being the chance of something happening, right? So if I say to you there's 30% chances of it raining today, so the probability that it might rain, right, would be equal to 30%, so that's 0.3. So we can represent probability as a decimal, okay? We can represent it as fractions, or we can represent it as percentages. So I can say 0.3 chances, or you can say 30%, okay? Or you can say the chance is 3 over 10. All of these mean exactly the same thing, right? So in this case, if I say to you there's a chance that it might rain, or that the chances of raining today is 0.3, then it means that the chances that it might not rain. So we always use this, we call this the complementary rule, right? So complementary rule simply says, if I know the probability of something taking place, then the probability of that thing not taking place would be 1 minus the probability of it taking place, right? So if I'm using rain, so if I'm saying the probability that it will not rain, so I use not rain as R dash, right? So then it means that this will be 1 minus 0.3, and so that will give us 0.7. Now you can think about it. If I say that there's 30% chances that it will rain, right, then it means that the chances that it might not rain are 70%, right? And that is all thanks to this guy called the complementary rule. So remember, right, that when we use the complementary rule, right, that a probability or a chance of something taking place, right, must always, or rather the chance of it taking place and not taking place must give us 1 at the end. All right, now, so this is the complementary rule, right? And I'm going to show you how to use that. So usually when they give us things like, tree diagrams, right? So if we draw tree diagrams and they tell you that if we are going to pick oranges, the chances that we might pick an orange, right, the probability that we might pick an orange from a tree, right, is going to be 0.27. Then automatically, what do we know? The chance that an orange might not be picked, right? So the chances of not picking, what should it be? 1 minus 0.27, and so this will be 0.73, right? So that will be 0.73. All right. So that is how the complementary rule works. Now, then we talk about independence. Now, guys, I want you to always keep this in mind. If we've got independent events, right? So if we say that events are independent, then what it means is that the probability, now I'll tell you what this means or what it looks like when we draw the Venn diagram, right? So the probability of, let's say, in this case, there are 2 events, that is event A and as well as event B, right? So the probability of A and B taking place, right? So if I say that those events are independent, then probability of A and B will be equal to probability of A multiplied by the probability of B. Please keep this in mind, right? We're going to do many questions that would require us to know this. So remember, if we say they're independent, then the probability of the one and the other taking place is equal to the probability, or rather the product of their probabilities taking place, or some stuff. So this has to do with independence. Of course, if they are not independent, then it means that this will not hold. Then the probability of A and B will not be equal to the probability of A multiplied by the probability of B. Right. And then also, now there's the general rule that we use, right? I want you to know this is the general rule of probability, right? So general rule of probability, what does it say? Well, you're given this formula. So it says the probability of A and B taking place, right, will be equal to the probability of A plus the probability of B minus the probability of A or B. Okay, right. Now, this is very important because they might tell you sometimes that, for you to calculate perhaps the probability of B, given that, A and B are independent events. Then, if they're independent, then you know that the probability of A and B would be equal to the probability of A multiplied by the probability of B. But now I want you to note, so I call this the golden rule, okay? So this would be the golden rule. Usually when they ask you to prove something, right, or for you to calculate either the probability of A or B, or sometimes the probability of A and B, they would have given you something that would help you towards the general rule, or in this case, what I call the golden rule in probability. All right, now, very quickly. So we talk about events being mutually exclusive, right? So these are events that will never meet. So what do we mean? So usually at school, they either ask you to do maths or maths lit, right? So there's honestly no student, well, at least in any normal school, that does maths and maths lit, okay? Or maths literacy, all right? Literacy, my literacy is going away. Right, so there's no student that would do maths and maths literacy, right? So what does that mean? It means that in this case, maths and maths literacy are mutually exclusive to each other, right? Meaning the chances of doing maths and maths literacy would actually be zero. So if I say to you events are mutually exclusive, it means that they do not meet in this case. So therefore the probability of A and B, if A and B are these two elements here, so the probability of A and B would be equal to 0. So keep this in mind. If the probability of A and B is equal to 0, then I know that these two events are said to be mutually exclusive. It means they do not intersect in any way, right? So they are mutually exclusive. Happy days. I hope that everyone is still well and really learning those very important things when it comes to probability. Listen to me talking about calculus. All right, let's get right into it. We're going to go into questions just now. But before I do that, now what would this look like on a Venn diagram? So if we're given a Venn diagram, right? So you're given your sample space over there, right? So suppose that I've got two events that are A and B, right? So note, what does this symbolize? So I'm going to use different colors just for us to know different things. So if I look at this, this is my entire sample space, right? Now, I want you guys to please listen very carefully. If I talk about the probability of A, right? Say this is my A element and this is my B element. This is another event, right? So where would I find the probability of A? So everything that would be in this circle, right? Under A, this would be the probability of A, right? And then if I say to you the probability of B, right? So let's take that again. So the probability of B, in this case, I'm going to indicate this with the red color, right? So I'm going to say, right, where is my probability for B? Okay, so everything under that that circle there, that element, right? So in that case, it means that I've got the probability of B in my red color, the probability of A in my yellow color. Now, do you see where I've got now the probability of A and B? This is where we've got an intersection, right? So probability of A and B, right? Where do I see this? This is where I've got an intersection between the yellow and the red color. Okay, so in this case, this is where I would indicate. I'll indicate it with the blue color there. So it would be in between those two over there. All right. So ladies and gents, when we talk about the probability of A and B, it would be the intersection over there. Now, I want you guys to please note as well, right, that if I talk about the probability, please note, probability of A or B, right? What happens in this case? It means it is the entire, now think about it, if I say A or B, right? So it means it would be the entire space. Now I want to try and demonstrate it to you very nicely, right? So it means it is this entire space under the two circles combined, right? So if I say the probability of A, now think about it. If I say A or B, right, it means I'm including both of them, right? So this would be it. It is the entire green space over there. So that is the probability of A or B, right? Whereas A and B was just strictly in the intersection. So when we looked at A and B, remember, ladies and gents, where was it? This was the probability of A and B, right? So this is where we had a intersection between the yellow and the red previously. Right, now, ladies and gents, I want you to note. So that means if I were to take the probability of A or not A or not B, where would this lie? So which means it's everything else that is outside, right? So I'm going to use a different color. So that means it's everything else that is outside of my sample space that is not within the circles, right? Now I want you to please note, I'm going to add another term now. So in this purple space, if we find that there is nothing, right, in that purple space, meaning that every single one of my events, right, falls within A and B, right? So in that case, we say that if the probability of A or B, meaning everything inside of my circles, right, gives us 1. Okay? Then what can I say? This is an exhaustive sample space. What do I mean by exhaustive? Right? It means there's nothing that is outside. So now I want you to think about it. If I go to a school, I will either find learners doing maths or maths lit, right? There's no way that a learner doesn't do either one of the two. So in that case, it means that maths and maths literacy are exhaustive events, meaning there is no learner that would not do either one of the two. Okay, right. So in that case, I hope that makes sense, ladies and gents. Right, we are going to look at some questions together, but quickly let's remember, what are the things that I need to remember? I need to remember that when I've got independent events, right, the probability of A and B will be equal to the probability of A multiplied by the probability of B, right? My general rule I need to remember, right? Probability of A plus the probability of B minus the probability of A or B. And then again, mutually exclusive events. These are events that would not meet. And so as a result, it means that the probability of A and B would be equal to 0. And finally, I told you or showed you how you can do all of those. And now we say that for exhaustive events, the probability of A or B should be equal to 1. All right, ladies and gents, I think we are ready to stretch our muscles and get into some questions together. Right, come on, let's get into the first example. So from a past exam question paper, they say events A and B are mutually exclusive. It is given that probability of B is equal to 2 times probability of A. Probability of A or B is equal to 0.57. Now, first of all, what do we notice? They're talking about the events being mutually exclusive. What do we know about mutual exclusivity? We know that probability of A, right, and probability of B, what will happen? We said if they are mutually exclusive, they do not meet, so it means that probability of A and B should be equal to 0, right? So we're going to use the golden rule of calculus here. They say calculate the probability of B, right? So in this case, we're going to say, right, so the probability of A and B, remember golden rule, is equal to probability of A plus the probability of B minus the probability of A or B. Right, so let's do that quickly. So probability of A and B, what do I already know? They're mutually exclusive, so that should be 0. Right, probability of A, right, this is what I want. No, actually I do have probability of, I'm looking for the probability of B rather. So they said that the probability of B is 2 times the probability of A. So I'm going to leave this as probability of A, right? And that means that probability of B is 2 times the probability of A, right? Minus, now remember they said the probability of A or B is 0.57. Now you must keep in mind we're looking for the probability of B, right? But in this case, I still have the probability of A. So I'm going to say, right, for the probability of A, I've got 3 times probability of A, right? So in this case, 1 plus 2 will give me 3, right? I'm going to take the 0.57 minus 0.57 and bring it to this side. Okay, and divide both sides by 3. And I find that the probability of A will be equal to, okay, so 0.57, okay, divide by 3. That gives me 0.19. But remember what they said about the probability of B, right? Probability of B is 2 times probability of A. So probability of B would be 2 times probability of A, which is 0.19. And what does that give us? This would be 0.38. So that would be the probability of B. Right, that's our golden rule. That is how we are going to apply it, right? Okay, so the next one says to you, we are looking for, in fact, they're giving us a box there of 40 calculators is sent to a store by a supplier. The owner of the store is not aware that 5 of the calculators are defective. 2 calculators are selected at random from the box, the first one not being replaced before the second one is selected, right? So I'm going to do this. Let's represent this as a tree diagram, right? So I'm going to have my first pick, right? So first pick, and I'll have my second pick. right? So in the first pick, what do I have? I'm gonna pick a calculator. Now there's a chance, there's a probability that it is, in this case, defective, right? And the probability that it is not defective, right? So I'm going to represent them that way. So in my first pick, they say to me, I've got 40 calculators and we've got 5 that are defective, right? So in this case, what is the probability that in my first pick I can pick a calculator that is defective, right? So that would be 5 out of the 40, right? So that is the probability that I might pick a defective calculator. Now, of course, what's the probability that it's not defective? It is going to be, well, how many are not defective? That means it's 45 out of that 40, isn't it? Right? So that's 45, not 45 rather, 35 over 40. So those are the ones that are not defective. Or you could have used that complementary rule. That's 1 minus 5 over 40. That would definitely give you 35 over 40. Okay, so that's on our first pick, right? Now, let's assume, so in our first pick, let's assume that we picked a defective calculator, right? So what would that look like if we picked a defective calculator, right? It means that if I picked a defective calculator here, right, then the number of defective calculators is less by 1, right? So now I've got, so the probability of the calculator, of picking another defective calculator. Now, how many calculators do I have left? It is going to be 4 defective, right? But out of how many? Out of 39, because remember, we are not replacing the calculators, right? So we're not placing them back, okay? Right, so in that case, I want you to note that the first one not being replaced, so it means that we don't put back the calculator after we have picked, right? Now, of course, what's the probability that it would not be defective? How many were not defective that were left, right? So if we picked one that was defective, we still have, remember, I've got 35 that are not defective. That are not defective. I've got 5 that were defective, right? So these were 5. So I've taken from this one, I'm left with 4, right? But now I've got 39 calculators, right? Now, if I'm left with 4 calculators and still the 35, then what are the chances of me picking one that is not defective again? So that would be 35 out of the 39. I hope this makes sense, guys. Right. Now, then let's focus on the next one. What if I picked a defective or a calculator that's not defective in my first pick? So again, right, the ones that are not defective are 35. The number that of the ones that were defective was 5, right? So now in this pick, if I picked one that is not defective, right? So that's minus 1. What do I have? I've got 34 that are left, but I still have those 5, right? So how many in total? That would be 39, right? And the ones that are not defective are 34 out of that 39. I hope that makes sense. So that would be 34 over 39, right? Now, this is the probability, this is the probability of picking not defective. In fact, let me, just for consistency, let's start with the defective ones, right? So for the defective ones, let's start all over again. If in my first pick, I picked one that is not defective, right? So that would be -1. So I've got 34 that are left. I still have 5 of that, right? So I still have the 5 of the ones that are defective, right? So we said in this case, what is the chance of me picking a defective one? It would be 5 out of the 34. So that's 5 out of, out of the 39 rather. Right, that's 5 out of the 39. And then what's the probability of me picking one which is not defective? So that would be, so note in this case, if I picked in my first one a not defective one, I have 34 not defective, right? And I've got 5 that are defective that are defective. So the probability of picking one that is not defective would be 34 over 39. Right, guys, I hope that makes sense, right? So we are using our complementary rule, right? Now they said to us, what is the probability that a calculator chosen is not defective, right? So that means that we're just looking at our first pick, right? So in that case, that would be in 11.2.1, right? How many calculators did we have, right? So the probability that a calculator chosen is defective, that would be 5 over the 40. Okay, right. So 11.2.2. They say to us, what is the probability that if 2 calculators are selected, one calculator is defective and the other is not? So we're going to pick, right? Now, please, I want you to note, how do I follow this on my tree diagram, right? So there are 2 chances of picking one defective and another one not. And how is that? If I choose a defective in the first pick, then I would choose a not defective in the second pick, right? So that's the first path. And then what's another permutation, right? It's choosing a not defective in my first pick and thereafter choosing a defective one in my second pick. Then I would definitely make it a point that, okay, let me just write this nicer. Okay, so let me just do this in the red, right? So red for danger. Okay, there we go. Right, so in this case, that would be the path where they are not defective. So what do I have here? I've got defective and not defective. Here I've got not defective and defective. Now, please note what's going to be that probability. It's going to be, right, so I'm going to say it's 35 over 40 rather, multiplied by, note, so it's 35 over 40 multiplied by 5 over 39. Okay, so I'm out of space there. So that's 5 over 39. Okay, so that's 5 over there. Right, let's just make some space. So that's 35 over 40 and multiplied by 5 over 39. Happy days? Right, so in this case, I know that for this one, what do I have? I've got 5 over 40. There it is there. 5 over 40 rather, multiplied by 35 over 39. Okay, so there we have those probabilities. So I'm going to say, well, firstly, it's going to be the probability of defective and not defective plus the probability of not defective and defective. Right, so this would be, we said, the first one, that's 5 over 40 multiplied by 35 over 39 plus, in this case I've got 35 over 40 multiplied by 5 over 39. I hope that makes sense, guys. That is how I would get that total. Of course, you can multiply them and get us the total answer. Okay, so that you guys don't complain. Okay, so that's 5 over 40 multiplied by 35 over 39. Okay, and plus, this is 35. So that's 35 over 40 multiplied by 5 over 39. Okay, right, so our final answer there would be 35 over 156. And of course, if you wanted to write it in decimal form, that's 0.224. Okay, right, so that is how that cookie crumbles. Right, so the last one, the last question here, they say to us, what is the probability that if two calculators are selected, both are defective? Right, so let's go on to our tree diagram again. So which path are we going to pick? Right, so we are looking for not defective, right? They said both are defective. Okay, so we are looking for defective. So notice on our diagram, where is defective? Right? So defective in the first pick and another defective in the second pick, right? So that's the only chance in which we can get both of them being defective. So that would be 5 over 40 multiplied by 4 over 39. So we're going to say for this guy, right, that's 5 over 40, so that's 11.2.3. So the probability of defective and defective, that would be equal to 5 over 40 multiplied by 4 over 39. All right, and before you complain again, let's find it. So that's 5 over 40 multiplied by 4 over 39. Okay, and that gives us 1 over 78. And that is the probability, as I did say, that you can represent it as a fraction. Right, and let's get into the next question on Venn diagrams. And now let's talk Venn diagrams. So I took this one from the Gauteng prelim, right? So let's look at it quickly. So they say to us, we've got two machines. Machine A and machine B are two different coin pressing machines that operate at the same time. The probability that machine A only presses a 5 rand coin is X. Okay, so there we see it in that there. So that's A only. So that means that that will be X. So, and the probability that it's B only presses a 5 rand coin is 0.3. So it is that area over there, right? So that's 0.3. And the probability that both the machines press the 5 rand coin at the same time is 0.1. So that would be the probability of A and B. This is over here, right? So in this case, we want to find out, okay, so they say if A and B are independent events. Now remember, what did we say about independent events, right? We said if they are independent, then it means that the probability of A and B would be equal to the probability of A multiplied by the probability of B. You must keep that in mind, right? So they say if they are independent events, determine the values of X and Y. Now, we know that the probability of A and B, right, is 0.1. Okay, that's 0.1. Now, the probability of only A, remember, only A in this case is is X. But remember, the probability of A inside here is this entire thing, right? So the probability of A in this case would be X plus the 0.1. Okay, you must keep that in mind, right? So so that's X plus 0.1, okay, multiplied by the probability of B, right? Remember, this is going to be 0.3 plus the 0.1 as well. So in this case, that would be 0.4. Remember, when we're talking about the probability of B, we said it is that entire thing that is inside there, right? So in this case, it means that the probability of B would be 0.4. So as a result, we can get the value of X rather from that. So that means that we can divide by 0.4 on either side. Okay, so that cancels with that. And so we've got X plus 0.1. Okay, sorry, this was meant to be 0.4 there, right? So X plus 0.1 will be equal to 0.1 over 0.4 will be 0.25. Sorry for writing it in such a clumsy manner, right? So that will be 0.25 equal to X plus 0.1. And so, which means the value of X will be equal to 0.35. All right, I hope that makes sense, guys. Right, so let's go to the next one. Or rather, we're looking for Y as well. Right, now remember, so in our entire sample space, we know that if we add everything that is within A and B, right? So if we add everything that is within here, right, plus Y, it should give us 1, right? Now, if everything within A and B gave us 1, it means that Y would be 0. And so we would say this is an exhaustive sample space, right? So, the events are exhaustive, right? So now we know that X plus 0.1 plus 0.3. So that's X plus 0.1 plus 0.3, okay, plus Y would be equal to 1. Okay, so Y would be 1 minus, so remember our X value was 0.35. Okay, I'm just going to place that value there. So that would be 0.75. So that's 1 minus 0.75. And in this case, that means Y is 0.25. I hope that makes sense, guys. So that means that this is not, or the events are not exhaustive, right? Now they say to us, determine the probability that exactly one of the machines is pressing a 5 Rand coin. Right, now, what are we looking for? We're looking for the machine to only be pressing, only one or the other of the machines should be pressing. So we don't want a situation where it is A and B. Okay, right, so in this case, we don't want that situation, but we want that or that. Okay, so in that case, can you see it's going to be the X, the 0.3 over there, right? And that is the probability that we've got A or B. So we can say the probability of A or B, okay, will be equal to 0. So X We said x is 0.35. So that would be 0.35 plus, in this case, we're looking at 0.3. So that will be 0.65. And there we have it over there, right? And that's how you would get the two together. Okay, right. So that is either A or B, right? It's not A and B. So that is how the cookie crumbles. Right, let's move on to our next question. Right, we're going to look at contingency diagrams or contingency tables next. So looking at question 11, they say to us, we've got a survey that was carried out amongst 210 people to determine whether they prefer watching rugby or soccer on TV. Right, they say the results are shown in the contingency table below. Right, now what I want you to note, contingency tables are probably the easiest of them all. Right, so look at this. So they said determine the values of A and B. Right, so with contingency diagrams or tables, so every time that I go vertically downwards, I will always get that total will be the total of females and males in that case. So it means it will be 72 plus 54. That should give me that total over there. So what will it be? So 72 plus 54 should give me 126. So already that tells us the value of B. That's 126. Okay. And then to get the value of A, again, we can look horizontally this time around, that if I take the number of females, it's split across the ones that watch soccer and the others that watch rugby. So 72 plus A should give us 120, right? So we're going to say 72 plus A gives us 120, and so A will be 120 minus 72. And what does that give us? Minus 72, that's 48. Okay, I'm doing this for the sake of time. So that's 48, and we said B would be equal to 72 plus 54, and this would give us 126. Right, now they say to us, give the probability that an individual chosen at random is a female preferring to watch soccer. So we go on to our contingency diagram and say, well, where are the females? There they are, right? So they are over there. So we've got females, and females that prefer to watch soccer right there. So it's 72 of them, right? Out of a total population of 210, and so that would be our probability. So this would be the probability of female and soccer. Okay, so that would be 72 of them prefer to watch soccer out of a total sample space or population of 210, and that is the probability. Okay, right, so 72, that's 72 divided by 210. This will give us 0.34. All right, approximately. I'll just leave it as a fraction. Okay, right, and then they say other events being male, right, and watch rugby, independent, and we need to justify our answer with a calculation. Now remember, so that's 11.1.3. So the probability of being male, and they said watching rugby. So watching rugby, right? So if they are to be independent, it means the probability of being male and watching rugby would be equal to the probability of being male multiplied by the probability of watching rugby, right? So what I'm going to do is, let's separate them. let's work out what's the probability of being male and watching rugby. So males that watch rugby. So there's our males that watch rugby. So that's 36 of them over 120. So that's 36 over 210, the total population size, right? Probability of being male, how many males do we have in the entire sample space, right? We are just looking at the males in total, so that's 90 over 210, and those that watch rugby in total, right, would be 84 over 210. So probability of being male, that's 90 out of the 210, multiplied by watching rugby, we said that's 84 over 210, right? I am correct. Okay, awesome stuff. Now let's work out those probabilities. What's 36 divided by 210? Okay, that's 6 over 35. Okay, and then we're going to take that product there. So we've got 90 over 210 multiplied by 84 over 210. Okay, again I get 6 over 35. What can I conclude? Therefore, right, they asked us, are the events being male and watching rugby independent? Okay, so therefore, yes, they are independent, right? Okay, being male, in fact, the inverted comma, and watch rugby, watch. Okay, see, this thing sometimes, watch rugby are independent. Okay, and why is that? Right, because the probability of male and rugby equal to the probability of male multiplied by the probability of watching rugby. Right, ladies and gents, this is the gist of it. Okay, I will leave my lesson here for now, and we'll see if we can add some more on probability. But ladies and gents, I tell you, if you just follow every single thing that I've done here, you should be more or less okay when it comes to the probability section. Next time when I come back, I will show you how to do the fundamental counting principle. Again, very easy, but let's do that next time. See you guys again. Sharp, sharp.